Hello, I'm Martin Waring and I'm a postdoc research associate at the University of Edinburgh. In this e-poster, I will be introducing the ITGC project Prophet and highlighting the importance of Earth observations for improving our understanding of ice sheet processes and making accurate future projections for sea level rise. Thwaite is in the Amundsen Sea region of West Antarctica. The drainage basin covers an area of approximately 200,000 square kilometres, and ice is approximately 1 kilometre thick at the grounding line where the glacier begins to float. Mass loss is particularly prominent in this region, with the Thwaites Glacier contributing approximately 1.4 millimetres to sea level rise each decade. This mass loss is increasing and is accompanied by faster ice flow and grounding line retreat. Numerical ice sheet models predict that this area is unstable and is undergoing runaway retreat. The International Thwaites Glacier Collaboration, or ITGC, is an international effort to investigate Thwaites Glacier with the aim of understanding the processes controlling its past and present, and also producing more accurate predictions about its future. The 8 science projects are split into 3 themes. The first investigates key processes, such as ice bed interactions, and uses a combination of fieldwork and process-based modelling. The second considers the historical context of present change and investigates past change in the region. The final 2 projects focus on using ice sheet modelling to improve understanding and predict the future of Thwaites. It is this final project, Prophet, that I will talk a little bit more about here. Prophet is a modelling project with the objective of reducing uncertainty in the near future projections of mass loss and sea level rise. The project aims to improve the representation of key processes that are not currently well characterised in large-scale ice flow models, including iceberg carving, ice damage, and basal melt. It is also looking to determine the relative importance of different external drivers of change. The project will use coupled ice-ocean models to make predictions of the future mass loss from Thwaites and its contribution to sea level rise on 100 to 500-year timescales. The project team will use 3 different ice flow models: ISSM, UA, and stream ice. Using 3 separate models will enable the team to encapsulate a wider range of uncertainty and help to identify areas where a particular model may need more improvement. Earth observations are key to producing accurate ice sheet models, as they provide both the input data required to initialize and drive the model, but also a validation dataset. For example, ice thickness and bed topography are important inputs, and this data can be provided by ice penetrating radar. In addition, ice surface velocity, ice surface elevation provides important information, and in the case of ice shelves, we can determine the ice shelf thickness under the assumption of hydrostatic buoyancy. However, there are a number of important unknown parameters, such as the bed slipperiness and the ice stiffness or rate factor. These unknown parameters can be inferred using a model inversion. With this method, additional observations such as ice surface velocity or elevation change are used as additional constraints on the model results. The unknown parameters can then be adjusted until the model reproduces the observations. Once the unknown parameters have been determined using this method, the model can be run forward in time to make more accurate future projections. There are further advantages to incorporating remote sensing observations into ice sheet models. Inversions are inherently ill-posed with multiple potential solutions, but by including all available constraints from Earth observations, we can reduce the uncertainty in the unknown parameters. Time series records can also be used to investigate the evolution of properties such as basal slipperiness or ice damage. Time series records can also be used to perform transient inversions, where the inversion process is repeated at the time each dataset was collected, with the unknown parameters corrected such that the model can correctly reproduce the trajectory of the evolution history. This method helps to increase the accuracy of unknown parameters by performing multiple inversions. It also ensures that parameters that are important for the current state and change of the ice sheet are accurately captured, and that parameter values that are potentially changing in time can be identified. To quickly summarize, ITGC Prophet aims to reduce uncertainty in near future projections of Thwaites Glacier. High quality Earth observational data such as ice speed, elevation change are vital for this type of project, and there is a need for datasets with both high spatial and temporal resolution. By incorporating these data into the modelling, we were able to improve projections of sea level rise around the world.